Okay, so we've gotten this far in the Carnot engine cycle table, and we're just wondering over here how we're going to fill these out. So, isothermal compression. It should be the same as what I did over here, except that I was given the work, and here I'm not. So, since I'm not given the work, I can't go find this volume that way that I did before. This is where the fact that it's a Carnot cycle, excuse me, is going to help me a lot. Do you recall in the description of the Carnot engine cycle we had, well, first of all, T hot, T cold, that's easy, but we also had Q hot and Q cold, right? So where in this table is Q hot? Have a look. Which cell would be labeled Q sub H for Q hot? It would be one that depicts the Q coming from the high temperature source into the engine initially, right? So it's that one, 163.00 joules. So this is the Q hot right here. This Q is 0, and I know that that Q is going to be 0 too, because those are both adiabatic steps. And so this is going to be the Q cold. Whatever this is the Q cold. So that's the T hot. Sorry, that's the Q hot. That's the Q cold. And this is the T hot. And this is the T cold. And there is a relationship in a Carnot cycle between or among all of these four. And it's related to the efficiency. And so I'm going to write it, get rid of this, and write it down for you. I need to make some room. And that relationship is that the Q for a Carnot engine cycle, oh dear, here we go, that Q hot, or some books call it Q high, over Q cold, and I'm going to take the absolute value because I don't want to get messed up with signs, is actually the same as the T hot over T cold. And if you look at your table, you've got Q hot, you have T hot, you have T cold, and there's only one unknown. Yeah, there's only one unknown. So, okay. And therefore, I'm going to move the camera a little bit here. Hold on. It's not lining up. Paper's giving shadows. I have too much stuff on my desk. There we go. So I can cross multiply and solve for QC. Q cold T hot is equal to Q hot T cold. I have my Q hot, that was the 163.00. I'm looking for the Q cold. TC, and that's all over the T hot. And so my QC is, that was 163.00 joules, My T cold is 125 K. And my T hot is 535 K. So my Q cold is in joules. 125 on 535 times 16300. And that is 3808 joules. Now I have to think about the sign. It's an isothermal compression. To figure out what sign it should be when I put it in the table, because I'm using absolute values there, so I neglected it. So I have 3808 joules. I go to my table, and it should go in here. Should it be a positive value or a negative value? This is an isothermal compression. Okay, think. It's isothermal, so delta U is 0. So heat and work are equal and opposite. And when you compress a gas, you have to work on it. So work will have a positive value. So therefore, in order to keep the temperature constant, we'll have to release that same amount of energy as heat. And so Q will be negative. So this is a minus 3808, but that gives me 4 sig figs. So really, this should be 3810 joules. 3810 joules. Okay, so there's Q. It is equal and opposite, the Q and the W. That's what they are. Okay, so that should be, I'm just checking my master copy here. Plus 3810 joules. So that is what makes these little calculations a little bit different than the straightforward Q and W ones. Yeah. So I wouldn't have that relationship between the two Q's and the two T's in a normal problem. I'm only able to do that because it's a Carnot engine. And we should do I'll fill it in green and then we'll actually work out the answer for entropy. It's still lacking. So entropy is going to be my value for work divided by the temperature. So we saw that, yes, it's the integral of dq reversible over temperature, but the dq reversible in this case is d work reversible. And I already have the number value for the work, so I pull it out of the integral sign and it becomes, and therefore delta S is equal to the work divided by the temperature. And so we can just go ahead and do that. Delta S for an isothermal process is simply equal to the work, which in this case is 3810 joules, divided by the temperature, isothermal temperature, and this one is isothermal at 125. So we have 3810 divided by 125 gives me 30.48. And the work was positive. Yeah, the work was positive because it's an isothermal compression. Yeah, the work is positive, but I want the negative value of the work because I'm looking for the Q. You see that? 3810 joules was the work. but we wanted the Q reversible. The Q reversible is the negative work, so that took a negative sign. And it makes sense in the end because, okay, yes, forgot to put it on, but then I questioned the value of delta S, particularly the sign, and it was positive, which doesn't make sense for a compression. You should be becoming less disordered if you're being compressed, right? So delta S should be negative for compression. So I went back, right, fix it, got it. And that's minus 30.5 in 3 sig figs. So a negative 30.5 joule per Kelvin. And what I like about this is that this next step, since it is adiabatic, and I know therefore that Q will be 0 and delta S will be 0, I know that for the cycle, the delta of a physical property has to be 0 for the cycle, which means that adding across here, my delta S's are going to add to 0, which is great. But I still wanted to show where that was calculated from. Okay, so we just have a little bit of work left to do here for state D and step 4. So this is an isothermal compression. So the way that you would find one of the, again, find one of these and then do PV-nRT to find the other. And recall what we did when we have the work for an isothermal change. The work is equal to minus nRT ln V final over V initial. And you realize that your V final for that process is your only unknown in that equation. Okay, so in the interest of keeping the video not too long, let me just point out to you that, so now I'm talking about the isothermal compression. Work formula is equal to minus nRT ln V final over V initial. And so whatever value I have for work, I could divide that by the negative of nRT, and that will be equal to the ln of V final minus the ln of V initial. And I'm looking to isolate V final. See, bring this back. I'm looking to get this guy. And so I have the work divided by the negative nRT. And I'm going to bring over the initial so it becomes positive. And I'm isolating for my unknown V final. I'll get a number, take the inverse ln, stick on the liters, and I've got my answer. So the work was a positive 3810 joules. That's divided by a negative 2.50 moles. I wasn't going to do this, but I will do it all out. What value of R? Right. Joule per kmol. We made that mistake already, so I have to make it twice. R, and then the T. What's the T? It's isothermal. Step 3 at the cold temperature 125. Plus the ln of 460. Don't put your unit in there. That's going to equal the ln of, whoops, the ln of V final. Okay, calculator going. So we have 3810 divided by 2.5 divided by 8.3145 divided by 125. Add to that, open bracket, 460 ln, close bracket, equals 4.66. I'll double check my sign, make sure that's done right. So the ln of VF, 4.6648. And so the inverse ln, therefore V final is inverse ln, or e to the x of that number, and that's 106. And I'm going to put the liters on it. Okay. 106 liters. And then PV equals nRT. Find your P. Blah, blah, blah. And I'm going to fill it in. I don't have to walk you through that calculation, for sure. PV nRT there, what is it? 206, 2.5. I'm looking for pressure. I think it's 0.242 atmosphere. Just PV nRT almost to get that result. Okay, we're almost at the end. It is just need that delta T, but we have it because it's a compression going from 125 up to 535. We know that work and delta U are the same, and so let's find out what that is. I can squeeze that on here. For that final step, work is delta U is NCV molar delta T. Our N, we know it's 2.5 moles. CV is, for this perfect gas, 3/2 R. And delta T, we also know it is heating up, so it's 535 minus 125. Okay, so I'll let you calculate that. I've done that on another sheet of paper here. And I have, for a value, I'm checking my other ones here at the same time. We had 12.8 kilojoules, but I've been writing joules the whole time. So 12800. And that is positive, it's a compression. 12800 joules. And, oops, sorry, hit the microphone. And then the delta H, the delta H is delta U plus NR delta T. We've got everything to calculate that. Check your answer with this one. I have 21300. There we go. Let's add things up. Let's see. So I'm just going to fold this over so we just look at the table values. I'm going to shade this in, indicating that those were all found. And I just want to say a few words about the table itself before we shut the movie. And just get it all in view. There we go. So, delta S for the whole cycle, this plus this plus this plus this, and it should be 0 for the cycle because it's a state property. Similarly, delta H should be 0 for the cycle, And if I add it up, it gets to 0. Delta U, same thing. Great. Now not for work and heat. In fact, that if the total Q and the total W are the same, then we're in business. We have a pretty good engine. And so let's actually add that up. So the work, I've got 163.00 minus plus 128.00 minus plus 38.10 plus 128.00. So minus 124.90 for the work, or in other words, the total work is a negative 12.5 kilojoules. So that's my useful work because it's leaving the system. So my engine can do in one cycle 12.5 kilojoules of work. That's good. And what about heat? I have 163.00 plus 38.10, which is negative. And that's 124.90 or 12.5. Right, because I added the cold. Okay, so 12.5 useful work. What is the efficiency? Last thing. What is the efficiency of this cycle? The efficiency is 1 minus the ratio of T cold over T hot. And so that's 1 minus 125 over 535. 0.766. That's not bad. That's excellent. Yeah, efficiency is usually given as a 2-digit percent, so say 77%. That's pretty good. Alright, so what we've done is to really draw out each step of this, but I would say that a really two important features of these questions are the following. Using work to find V final, and using the relationship between Q hot, Q cold, T hot, T cold to make our way through here. Okay, when we were left with two unknowns here, and we used that to find the Q cold and then continue. So those would be the two features that I would say are important here that make this question stand out from the regular questions of finding Q, W, del T, del H, del S, etc. Great. Okay, good.